So in the last session, we talked mainly about partition. We talked about a replication, how the replication is maintained, and we talked about the leader copy and the follower copy. The replication itself is called as the follower copy, and the broker which is hosting that follower copy sometimes is also called as a follower broker. We saw all those stuffs and how the replications are done. We also saw that. Similarly, we talked about how a producer comes to know where the leader copy exists, because the data transmission always happens through the leader copy or the broker which is hosting the leader copy. So the producer comes to know through the metadata request, and it starts sending the data to these brokers which are hosting the leader copy. And also we saw how the leader election happens. If at all the broker which is hosting the leader copy goes down, the communication stops. So there should not that should not happen. To make sure that the leader is always up, again leader election happens with the help of the zookeeper. So we saw all these things in the last session. Along with that, we also saw messages are sent how the messages are sent using either a round robin fashion, hash partitioner, uh, either it use a hash partitioner or specific partition you can specify, or you can use a custom partitioner. So that's how the messages are sent. And and we also talked about batches, how batches are created and sent, and what is batch size and batch linger millisecond. So these two configurations also we saw. Again we saw about the number of partitions, and there was a slight miscalculation. So I will try to explain it today. So before that, let's see. There could be multiple number of, sorry, just a second. So we'll talk a bit on more on the producer here. So there could be three types of producers. Something is happening to my pen tablet. So we have fire and forget producer, synchronous producer, and one more is asynchronous. So these are the three types of producer that we have. Now what do we mean by fire and forget producer? Fire and forget producer means this producer just sends the messages, and it doesn't worry about whether that message has been received by the broker or not. So that's what we mean by fire and forget. Sends messages, does not worry whether it's reached. Whether these messages reached broker. So these producers are fire and forget producers. So what can happen is here we can have a data loss. There could be a data loss because the producer doesn't know whether these messages are sent has been received by the brokers or not. So whatever code yesterday I showed, those are all that code is fire and forget producer. Now we have one more kind of a producer called synchronous producer. What are synchronous producers? Synchronous producers are the producer which block itself blocks itself and waits for acknowledgement. So these are all called as synchronous producers. So the synchronous producer will send a batch of data. It will send a batch of data and it will wait there. It will block and it will wait. I mean, it will not return from the function itself, and it will wait until it receives a acknowledgement from the broker. So here the data loss will not be there, but you can see that since there is a waiting, obviously the latency will increase for that message. There will be a high latency for every message because before sending every message, it has to wait for the previous message's acknowledgement. But it will be durable. The data loss may not be there, but there will be a high latency. I mean, these two are some kind of extreme ends. Fire and forget and synchronous are two extreme ends. Can we have in between something so that there could be a slight data loss and there should also be not high latency. If there is a low latency, if we could bring down the latency, and if it's also okay to lose few of the messages, is it fine? Somewhere in between, so we call it as asynchronous producer. So asynchronous producer, what it will do is it will not block, it will not block, it will register a callback for handling acknowledgement. It will send the messages, it will keep on sending the messages, and it will not wait, or it will not block and wait for the acknowledgement from the broker. It will register, instead it will keep on sending messages, but underneath there will be a callback registered. As soon as the acknowledgement comes, that callback will be called here. So as you can see here, it is not blocking itself. So it is this asynchronous producers are in between some fire and forget and the synchronous producers. So code wise, how can we say that it is a? So if you open the producer example, so again just keep a note on that: downloads, training, Kafka examples, producer example. Most of the Kafka related code are in this. So just a simple producer. If I see a producer example here, we have already seen a normal producer example. There is not much difference here. You create a producer object, you create a producer object, and you call the send method. You create producer object, then you create producer record object, and using that producer, send the producer record using the send method. So this, if we write this piece of code, this piece of code just says that it is fire and forget. If we just use send, the send itself says that it is fire and forget. How different than how the synchronous producer looks like. There is only slight difference in the synchronous producer. So synchronous producer, everything remains the same. After send, we call the get method. So this get method will not return. You will not, the execution will not return from this get method until it receives a acknowledgement. It will block. This get method will block until it receives an acknowledgement. If the acknowledgement says that message is message has been transmitted to the broker, so it will give you the to which partition number it has been sent. So it will return the partition number and the offset. Offset we have not seen it. We have to see it. So if the I mean to say, if the message has reached the broker, it will return in the form of acknowledgement. It will return to which partition the message has been sent. Otherwise, it will throw an exception. In case of any exception, it's your duty to handle what should be done here. Based on your business logic and all, it's your duty to handle this. Now this is your synchronous producer. That's all. Just use a dot get. It will block itself. Now how do we write a asynchronous producer? As I said, asynchronous producer is again it will register a callback. So we have to write that callback. So if we see here asynchronous producers.java, so when here everything remains the same, but the way we are sending the message. Using the producer object, this is the producer record. A new thing we are writing, we are saying my producer callback. So we have to write this callback. So callback is defined here itself. Callback is a class again which implements the callback interface. This is our callback, and which implements callback interface, and that callback interface has on completion method. So this method will be called as soon as an acknowledgement comes. So that's this method will be actually registered. So here there is no blocking. This will not block. It will keep on sending the messages. But if it wants to handle the acknowledgement also, so it will register this callback, and whenever a acknowledgement comes, this callback will be called. On completion will be called here. So these are the ways you write a different producer based on your business needs. If you are okay to lose a bit of a data, if you are getting the messages from Twitter, it is okay to lose some of the data. If you are getting the data from some GPS locations, it is okay to lose few of the coordinates. So in that case, you can go for fire and forget. Synchronous producer is all about you don't want to lose even a single message. So in that case, you can go for synchronous producer. Asynchronous is all about sometimes you lose it. I mean, you don't want to block yourself. Here you will not lose the data, but there will be high latency, because you will be waiting, you will be blocking and waiting. So you don't want high latency in your application. You want to reduce the latency of every message. You can go with the asynchronous producers. So these are all the different kinds of producers we can have. So I hope these things were clear. Now there are certain parameters we need to get used to. I mean configuration parameters. Yesterday we saw batch size. It is a threshold after which the data will be flushed from the buffer of the producer. And we also saw linger.ms, which is usually 1 millisecond or something, which will send the messages as soon as that timer expires. In a similar fashion, there is a acknowledgement. There is a ACK configuration. All these are producer side configuration. So this ACK has multiple values. ACK has multiple values. ACK equal to 0 or ACK equal to 1, ACK equal to all. Now what do we mean by ACK equal to 0? ACK equal to 0 means the producer is saying to the broker that that I don't expect any acknowledgement from you. You need not send any acknowledgement for me. So that's what ACK equal to 0 means. You have your producer here, you have your producer, and let's say we have our brokers here. Broker 1, broker 2, broker 3. Let's say we have sensor hyphen 0. I will not take other partitions, will only take the replications. Let's say there are 3 replications. There could be different number of partitions. I'm considering only the first partition, and that partition has 3 replications. So in your producer code, if you say ACK equal to 0, so what it means here is that producer sends, we know that producer sends message. Here, let's say this is the leader copy. These two are follower copy. Producer sends the message to the broker one, and it says to the broker one that you need not send me any acknowledgement. Whether that message has been received or not received, you need not say me that. So ACK equal to 0 goes well with fire and forget API. ACK equal to 0 goes well with fire and forget API. Because fire and forget producer, what it does is it will not check whether it has received any acknowledgement or not. So there could be a data loss here, because since it's not expects any acknowledgement, the data might not have been received by the broker. The data might not have been, because the moment a message arrived, at that point of time the broker might have gone down. Out of few messages, out of lot of messages, few messages may not be received by the broker. I mean, we need to keep that in mind. Data loss may happen only if there is a some network issue or the broker has gone down. Otherwise, there will be no network data loss. Data loss usually happens if the broker goes down. At that point of time, some messages were there in the network and they were not reached to the broker. So that's what we mean by data loss. So since that acknowledgement is not there, there could be a data loss with ACK equal to 0. Now when I say ACK equal to 1, what it means? When we configure ACK equal to 1 here instead of ACK equal to 0, what it means is the producer will now say to the broker that as soon as you commit the message, meaning meaning as soon as the broker will have to write the message to the file. It has to write that append that message to that .log file. So as soon as you commit that message, you send me an acknowledgement. You send me an acknowledgement. So that's what ACK equal to 1 means. The leader will be sending the acknowledgement. So leader will be sending the acknowledgement. Here it goes well with asynchronous and asynchronous. The in the both the cases, the producer will be expecting an acknowledgement. Synchronous goes well with synchronous and asynchronous. Here also there could be data loss. With ACK equal to 1 also you can have data loss. How is that possible? How is that possible? So let's say this broker has received message 1, message 2, message 3, message 4. Now how the replication is maintained? We know that broker 2 will contact broker 1 and it will ask for the messages. Similarly, broker 3 will also contact broker 1 and it will ask for the messages that it has committed. So let's say broker 2 and broker 3 are not as fast as broker 1. They are a bit slow. They are a bit slow. So broker 2 has consumed up to 3 messages. It has not yet consumed the fourth message. Similarly, let's say broker 1 and similarly broker 3 has consumed message 1 and message 2. It has not yet consumed message 3 and message 4. At this point of time, let's say broker 1 is down. At this point of time, let's say broker 1 is down. So it is not yet committed. It is not yet committed. I mean to say it has been committed. Hence, the acknowledgement has been sent here by the broker one. But message 4 is not yet copied here. Message 4 is not yet copied. Now we know that as soon as a broker goes down, which is now a leader broker for partition sensor 0, obviously leader election will happen among with wherever the follower copy exists. So since broker 2 has more latest messages, broker 2 has more latest messages, so broker 2 will be the leader now, or or it will make its copy as the leader copy. Now the communication happens if you have a consumer here. Now consumer will be contacting this broker for data. Yes, messages in B2 and B3 are the replicated messages. So B2 will ask for message. B2 and B3 will ask for the messages, and B1 will send the message. Broker 1 will send those messages. That's how the replication works. Now since broker 1 is down and broker 2 has not yet received message 4, so you can say that message 4 is lost. Now all the communication happens through broker 2, and I mean the producer and the consumer communication happens to the broker 2, but broker 2 was not able to be copy the all the messages from broker 1. So there could be still data loss. With ACK equal to 1 also, there could be a data loss. Now that's the reason there is one more option called ACK equal to all. When we say ACK equal to all, what it does is it says to the producer, the producer says, it conveys that I need acknowledgement from all the brokers which host the copies. I just don't need acknowledgement from just the leader broker. I also want the acknowledgement from the follower brokers. So the producer will send the message to the broker 1. Broker 1 will commit that message to the log file. Broker 2 and broker 3 will ask for the messages. They will ask for the messages. These are all asynchronous. They will ask for the messages. Broker 1 will send the messages to them. They will write down these messages, and after writing, they will send an acknowledgement back to. They will after receiving the message, they will send the acknowledgement. Once the leader broker receives acknowledgement from all all the brokers, so then it will send the acknowledgement back to the producer. Yeah, here is a question. If in between, when the partially has gone to the other broker, so again we can't do anything here. We can't do anything. There could be some of the data loss. There could be possible. So that's how the things work. So those cases that you have, that case, it's very rare case. That's a very rare case, but you can be sure that with ACK equal to 1, we try to achieve high durability. We try to achieve. So these are the again this goes with synchronous and asynchronous. ACK equal to all goes well with synchronous and asynchronous producer. ACK equal to 1 also will go well with synchronous and asynchronous producer. ACK equal to 0 goes well with data loss. Goes well with fire and forget producers. So these are the different three types of producers, as well as a bit of a configurations on the producer side. There are other configurations as well. Along with these, there are other configurations as well, with the producer side. So I hope you got a bit of an idea more on the producer here, how the producer looks like. Now I will try to give a brief on optimizing Apache Kafka. So all these documents are there in the Google Drive. So in the training, if you go to Kafka, in the Kafka you can download this kafka.rar. This rar file will have all the details. The documents will also be there. So this also you can check. This will also be useful, but most of the documents are in this rar. You can extract this and you can get the details. So here there are certain service goals that has to be kept in mind before you are developing any Kafka application. So these are all the service goals: high throughput, throughput, latency, durability, and availability. Now you can achieve one of these. You cannot achieve all the service goals. You have to compromise on one or the other, or there will be always a trade-off between one or the other service goals. So you have to sit with your team and discuss what we want to achieve. Now what is throughput here? Throughput is nothing but the rate at which data is moved from the producer to broker or broker to the consumer. End to end, how many messages are transmitted per second. So that's the throughput. Number of messages per second. That's what we call as throughput. More the messages per second, so higher the throughput. Similarly, what do we mean by latency? Throughput, latency, they are almost related. They a bit get confused. So latency is nothing but time taken by a single message from the producer to the consumer. It is time taken by single message. If a single message reaches in milliseconds, it is a low latency. If a one message takes like 2 or 4 seconds to reach the other end, so it is a bit of a high latency. So throughput, you can say number of messages per second. Latency is with respect to per second. Time taken by single message. That's what we call as latency. Similarly, we have durability and availability. Again, this durability and availability will be a bit confusing. So durability is nothing but it's all about reducing the chance for a message to get lost. It's all about, so we can see that we saw here making ACK equal to 1, making ACK equal to 0, you have high probability of losing a message. By making ACK equal to 1, so you have a bit lower probability of losing a message. If you make ACK equal to all, you again reduce the probability of losing a message. So durability is all about that. Durability is all about reducing the chance for a message to get lost. That's what we call as durability. Now, what is availability? Availability means even if there is something wrong going on, even if something wrong happened, even some node has gone down, there could be a data loss, but how fast you will be available for the client. That's what we mean by availability. Minimizes availability is all about minimum downtime in case of unexpected failure. Whenever an unexpected failure happens, there could be a data loss. Durability may be compromised, but are we good enough to come back again and serve the clients? So clients should not suffer here, even though there may be some data loss. So as you can see here, availability and durability are slightly connected. Latency and throughput is also slightly connected. There is a thin line between the difference here. So you just need to keep in mind these things. So there are certain configuration parameters that can be used to achieve all these steps. I mean, few of the steps can be achieved. Now, what do we mean by throughput? Throughput, I said that the number of messages transmitted per second. More the number of messages transmitted per second, more the throughput. So obviously, if you have more partitions, more messages can be transmitted per second. So yesterday we did a miscalculation here. Miscalculation here. Uh, 10K into 2000 is actually 2 MB, 20 MB. We somehow made it as 2 GB. I don't know. I made a mistake there. So we went to 2 GB, I think. So it is 1K into 1000 equal to 1 MB. So this mistake we did. I mean, in fact, I did the mistake. I said this. This is wrong. Actually, 1 KB into 1000 is 1 MB. So the idea is you can think this as a thumb rule. You can think this as a thumb rule. Each message is around 2 KB. Each message size is around 2 KB, and and each part number of messages per trans messages is 10K. 10K messages per second per partitions. Around this, you can have 3 KB messages, probably 9,000 messages, somewhere around you can do the. This is just a thumb rule, just a starting point you can think of. Each partition should be able to handle 10,000 messages per second I mean, per partition. And each message, if it is a size of around 2 KB, you will get a good throughput in your Kafka cluster. So if you have such a thing, so obviously 10K into 2K equal to 20 MB. Meaning a partition can handle one partition should be able to handle 20 MB per second of data. One partition should be able to handle 20 MB per second of data. So if your application requires, so application requires 1 GB throughput, meaning 1 GB per second. If this is the requirement, 1 GB per second, so how many partitions you would be creating? 1 GB divided by 20 MB, which is equal to 50 partitions. So that's how you compute the number of partitions for your applications. So if you are expecting 1 GB of a throughput per second, then around 50 to 100 partitions should be there. I mean, for you may get hikes, spikes at some time. So you just have somewhere between 75 partitions is also fine. 75 partitions is also fine. So that's how you give the number of partitions. So yesterday we made a mistake. This is usually how the number of partitions are computed. That's a thumb rule. So you just keep in mind that this could be taken as a starting point. Then you start experimenting, start increasing the number of events per second, keep decreasing the partition or increase the partition, and check where you find, keep increasing the size of the message, decreasing the size of the message, then check where you find the perfect point. So I hope the number of partitions is clear here, how to compute the number of partitions. So as we can see here, if we increase the number of partitions, obviously we can handle more throughput. If we have more partitions, obviously we can handle more throughput here. So that's what we have to. So if you want higher throughput, you need to have more partitions. You need to have more partitions. Again, batch size. Batch size, we know that it controls how many bytes of data to collect in the buffer before sending the messages to the Kafka broker. Yesterday we discussed this. Now default size is some 16,000 bytes. 16,000 bytes. This also could be managed. Linger milliseconds also we discussed here. Collect the data for this much of time and then send the message. Collect the data for linger millisecond time and then send the message. Now how it will affect the, what configuration should be given so that you get higher throughput. Increase that from 16,000 bytes. I mean, this is again, you can also experiment here. The idea here is this: if you increase that size, obviously more message will be accumulated in the buffer. More messages will be accumulated in the buffer, and more messages will be sent at a time to the broker. And it may be a bit confusing, but we achieve higher throughput. So this is your producer. So in your producer, if your buffer size is bigger, so more messages will be accumulated here. Message 1 to message n. Message 1, more messages will be accumulated in the producer. Only then it will be flushed to broker. what we are doing is we are sending more messages at a time. We are sending more messages at a time, we get the higher throughput. Now, what the broker, if you are sending one message at a time, let's assume let's assume we are not sending more messages at a time. Let's assume we are sending only one message at a time. So as soon as one message arrives, inside the broker there will be threads. There will be threads that will use that will take that message, write it to the message queue, and it will be flushed to the disk. It Those threads will be working for every message. I mean, instead of a thread works on a bunch of messages, a thread working on a single message. A thread working on a single message will take a more time because every message individually it has to do that. A thread working on a bunch of messages at a time, it will have a more throughput. It will have a higher throughput. So that's what we are trying to say here. More messages are processed at a time. More messages are sent per second. So that's how you increase the throughput. That's how you increase the throughput. So more the batch size, more messages will be accumulated and it will be sent at a time to the broker, hence the throughput increases. Similarly, if you increase the linger millisecond, so by default it is 0, meaning as soon as a message is there in the buffer, send it. As soon as it receives a message in the buffer, send it to the broker. If you increase it to 10 to 100 milliseconds, it may have multiple lot of messages accumulated in the buffer, and then it can send it. So that's how you increase the throughput. Increase the throughput. There are also compressions. Default there is no compression, but you can also compress. I mean, before sending the messages, a batch may be compressed. A batch of data will be compressed and sent. So more messages will be sent if you compress the data. I mean, in the buffer, there will be lot of messages available. Still room will be available. If you compress the messages, if these messages are compressed, still more buffer will be, free memory will be available. You can still keep on sending, accumulating the messages. Hence, compression will also help for higher throughput. Higher throughput. Acc equal to 1, acc equal to 1, it just, or acc equal to 0 is also fine. Acc equal to 0, or I think acc equal to 1 should also be fine, because it will not wait. In this case, it will not wait for the acknowledgement. It will not wait for the acknowledgement. It will keep on sending the messages. Acc equal to 1, it will only wait for the leader's acknowledgement. It will only wait for the leader acknowledgement. Slightly the throughput will be low, but good enough. But it will be good enough. Now that there are retries configurations also available. Retries configuration also available. So let's check it there. So yesterday we saw this, right? Yesterday we saw that. Yesterday we saw that a batch of data will be sent to the broker. So if acc equal to 1, I mean, if here you said acc equal to 0, acc equal to 0, the broker will not send any acknowledgement. No acc will be sent by the broker. But if acc equal to 1, acc equal to 1, so the broker will send a acknowledgement. Now that acknowledgement, it could be, I mean, this acknowledgement may receive or may not receive. Sometimes this acknowledgement may be lost. Something could happen. So in that case, so the retries will happen. If any failure and if the retries is configured, a batch of data will be retried. Internally, internally the retries is already taken care. We don't have to worry. 3 times I think the retries will happen. If it does not receive any acknowledgement, so in that case, based on the number of retries you can configure, so a particular batch of data will be resent. Particular batch of data will be resent. So again that will also, if you are resending your messages once again, obviously that will also affect the throughput, because you are not sending new messages, we are sending the older messages itself again and again because of some failure. So that will also affect the throughput, hence retries will be set to 0. Retries will be set to 0. So all these configurations helps us to achieve higher throughput. Higher throughput means more messages per second. Now buffer memory is your this is your buffer memory. There is a difference between buffer memory and batch size. They are not same. Batch size and buffer memory are different. You can assign buffer memory to be uh, uh, probably 1 GB. Usually it is in MB. Let's say 10 MB. Buffer memory could be 10 MB. Your batch size could be 1 MB. As soon as 1 MB of data is being accumulated in this buffer, you flush the data. But buffer memory could be more than that also. More than that as well. Because you can always get more and more data. More and more data. So buffer memory is your total size of your buffer. Batch size is just to determine when to flush the data to the broker. So you can have increase if there are a lot of partitions. So this is the producer side configurations. We will see the consumer side also, but we haven't discussed the consumer side. But did we observe here that all these things increases the throughput? All these things increases the throughput, but the latency will be high. But the latency will be high here, because what is the definition of latency? Latency is nothing but the time taken by a single message to reach from source to destination. Now since we increase the batch size, more messages will be accumulated in the buffer. Since we increase the linger millisecond, more messages will be accumulated in the buffer. So those initial messages will not be sent until the batch size reaches, or until the linger millisecond timer expires. So those messages will be waiting here. Obviously the time taken by those messages to reach the end is more, so you'll have high latency. As I said earlier also, you cannot achieve all the 4 service goals. So you have to decide which service goal you want to achieve. So do you want high throughput? Then you have to compromise on the latency. You have to compromise on the latency. Similarly, setting ACK equal to 0, you get high throughput, but there may be data loss. Durability will be compromised here. Durability, because we know that the data may, you don't care whether the message has been received on the other end or not. So I hope these things are clear. For high throughput, low latency, all these things are the configurations. So whatever I have explained here, it is just a summary of the actual document. So you can find the actual document, optimizing your Apache Kafka development and Cloudera Kafka reference architecture. These two PDF files are very good PDF files for Kafka. I mean, they does not explain the basics here. They explain very in depth of how to optimizing your Kafka cluster, how your Kafka architecture should look like. It doesn't explain anything basics for the beginners. This document is not for the beginners, but it is a very good document. I would suggest to go through this document for better understanding of the architecture of Kafka. So as we know that, as we talked about throughput, similarly latency. Latency, as I said, time taken to move message end to end. Default values are optimized for low latencies. Not much changes are required here. As you can see here, these were the changes we had to do. As you can see, linger milliseconds was 0, meaning as soon as the message is available in the producer buffer, send it. Don't wait for any expiry of the time. So by default, most of the values are configured for low latency. So as we know that more partition increases latency. More partitions, we know that will increase the throughput, but every time the copy has to be made. More the partitions, more the copy has to be made here. So it will take time to make the copy. It will also take time to replicate more partitions. Can increase. I mean, so there are some threads can be, these are in the, I haven't seen this num replica fetchers. I haven't seen this, but we can search for this and check this. Similarly, linger dot millisecond, set it to 0. Obviously, it will be 0. Acts as 0, send, keep on sending the messages. And fetch min bytes, this comes on the consumer side. So we are yet to see how the consumer works. Linger millisecond, these are all the producer side configurations. Num replica fetches is on the broker side. So these are all the broker side configurations. So all the broker side configurations will be in the server.properties. So I had not seen that configuration. So server.properties, num network threads I have seen. Sometimes you have to also increase these things. Num network threads and num IO threads. So IO threads are used to write the messages to the uh, uh, log file. I mean the .log file, if we have seen where the messages are appended. So IO threads are used for that. num network threads are used for fetching the data from the leader copy. So that from the from so broker 2 has to ask broker 1 for the newly arrived message. So those will be done by the network threads. Broker 1 will be sending the messages to broker 2. So those will be again done by the network threads. I don't know fetch where it has come. Probably it is based on this only. How many number of network threads? Number of these things also needs to be configured based on how many fetches you are doing. How many fetches you are doing. So these are also important. So to showcase the diagram, one more diagram I have. So you have processor threads where this is your IO threads. So your connections are coming here. This is your broker, some broker. So these connections may be coming from a producer. These connection can be coming from a internal another broker. These connection could be coming from an external consumer. So here the connections could be from the producer. Producer may be sending the data. Broker may be asking for the latest message. Consumer will be consuming the data. These connections are from different entities. So those messages, I mean, a processor thread will handle a message and it will send that whatever request has come, it will send to the request queue. IO thread will take that request queue, the message from the request queue, and it will send it the message to the. It will commit that message. I mean, not only that, sometimes the request may be to give the message. If the request if the request has come from the producer, if the request has come from the producer, it is sending the message. That message will be put in the request queue, and the IO thread will take that message and it will commit it. If the request is coming from a broker or a consumer, it is asking for messages. Again, that request will go to the request queue. The IO thread will get that message from the logs, from the disk log, and it will give the response. And that's how the cycle happens. So more the number of threads here, more the number of threads here, more throughput or higher throughput can be achieved. Higher throughput can be achieved. And also low latency can be achieved. That's how these things help. These things help. That's the reason a single broker per system is good enough. In one system, one broker is good enough. One daemon is good enough because internally lot of threads will be there which can handle lot of partitions. So you do not require more brokers per system. One broker is good enough, and these are the configurations that has to be changed for higher throughput and lower latency. Number network threads, number of IO threads. So I think I don't remember that in one of that reference, one of this PDF. I think in this Cloudera PDF they have explained how many threads should be there, how to choose the number of threads, IO threads, and the number of disk threads. So I hope those things were also clear. For lower latency, what all should be done. We will come to this min fetch bytes as well. We haven't seen anything about the consumer. We have to still see how the consumer looks like. We have only seen the broker part. We have only seen the producer part. We still need to see the consumer part. Similarly, durability here. For higher durability, obviously we need to have more replications, and also so set acks to all, and also set retries greater than 0. So these things you have to. I'm not much aware of this rack here, and unclean leader election. It's slightly indicates whether brokers. There is something called as in sync replica. So I did not say anything about the in sync replica. So we know that replica is, if you have a replica of three copies will be there. Now what do we mean by in sync replicas? In sync replicas means which are in sync, which are exactly in sync. I think so. Here minimum, they have said minimum in sync replica. Replication equal to 3. In sync replica. Minimum in sync replica is 2. So there has to be, it means that there has to be at least two replicas. There has to be at least two copies which should be in sync. I mean, we have sensor 0, and one more sensor 0. Three replicas. Now at least two has to be sync. One will be usually the leader copy. There has to be at least one more which should be in sync to this replica. In sync to this replica. So in that case you are in sync. These two are in sync. So that helps in that case, whichever is in sync, whichever broker is in sync, whichever replica is in sync, the broker hosting that replica will be chosen as the leader. I mean, it all comes to when you are choosing the leader. If the leader goes down, if this broker goes down, the in sync replica will be chosen as the new leader. So you always need to achieve in sync replica, meaning act has to be set to all. With act equal to all, you will most of the time you will have in sync replicas only. Most of the time you will have in sync replicas only. So choosing a leader from a synced replica will not have any data loss. That's what we mean by in sync replica. And there is something called as unclean leader election. So this has to be set to false. uh, uh, Unclean leader election means, so you can think of this as a clean leader election. Now these two are sync synced up linear replicas. Both has the same number of messages. There is no data loss. So you chose whenever broker 1 went down, broker 2 was chosen as the leader. Broker 2 was chosen as the leader. So this we call as a clean leader election. Clean leader election. If B1 is chosen as the leader, if B1 is chosen as the leader, B1 may not have, I mean, it will have, if ACK equal to 1, if ACK equal to all, broker 2 will also copy, broker 1, sorry, broker 3 will also ask for messages. Broker 1 will send the messages to these brokers. They will make a up to date. All are having up to date messages. So your in sync replica are more than the minimum. All are in sync. All are in sync. Broker 1, broker 2, broker 3, all are in sync. Minimum requirement is at least 2. This is what the restriction is put on. Minimum requirement. At least 2 should be minimum required. But we can be sure that in ACK equal to all the brokers will be in sync. All the brokers will be in sync. Choosing a leader from a synced replica is called as a clean leader election, because there will be no data loss at all. Let's say broker 3 was not in sync. Broker 3 was a bit lagging behind. Broker 3 was bit a lagging behind. Then choosing a leader as broker 3. If broker 1 went down, in that case broker 3 is chosen as the leader. Broker 3 is, because since it is not in sync, since it is lagging behind, and still this has been chosen as the leader, it is called as unclean leader election. So you need to disable that unclean leader election. You have to disable unclean leader election. That's what they are saying here. Unclean leader election enable, make it as false for higher durability. Because it may happen that a leader may be elected from the replica which is not yet synced. Which is not yet synced. It may be this. So when we make it unclean leader election enable false, so the leader will be selected from a synced replica. From a synced replica. So I hope that, so these things has to be taken care for higher durability. I mean, lot of configurations are there. Replications set to 3, ACK equal to all, retries. We know that as in we more retries, we can be more durable. This we will discuss this. I mean, it's not so important. We'll see what is this later. Similarly, on the broker side, default replication we can set it to 3. I think this why did it come here? Default replication factor. This is on the broker side. So there are certain configurations we have to set it to false. Auto create topics are there. I mean, those things we have to set it to false. Min in sync replica set it to 2. Unclean leader elections set it to false. So these things we have to keep in mind. Now there is something called as log flush interval message. This is also very important, but it should not be touched at all. It should not be touched at all. Now, what do I mean by this log flush interval message? I mean, this, forget about this service goals. There is very important thing to remember here. So overall architecture, if you take, we have producer, we have a broker, dot log for sensor hyphen zero. In the sensor hyphen zero, we have this file and we have our consumer. Now producer sends the message, we know that, to the broker. Broker appends that messages to this file, and consumer asks for messages. Broker will get the message from here. Broker will get the message from here and send the message to consumer. Now when the disk is involved, when disk is involved, can we achieve real time data transfer? Can we achieve real time data transfer here when the disk is involved? Obviously there will be lot of latency whenever the disk is involved. So you cannot achieve real time processing or real time data transfer in the message queue when the disk is involved. Then how Kafka is suitable for real time processing? Why Kafka is used for real time processing? Any guess on why it is being used? Even though it is a persistent message storage, why it is, how it solves the real time data processing, and why it is used in the real time data processing? Any guess, anybody? Any wild guess or anything that you have in mind? So it's all on the operating system. Right, disk processing is slow. Disk processing is quite slow, but still Kafka is used in real time. Still Kafka is being used in real time. Even though the data is being flushed to the disk, how it is being handled in the real time. Why it is suitable for the real time. The idea is this. Idea is this. So any application if you take, forget about Kafka. Any application writes to file. When any application writes to file, the application only writes to kernel page buffer. So application doesn't know whether the file is being returned to the message or the data has been returned to the file. Anything, if you open a file, read a file, open a file, write a data to the file, your Java code is not actually writing to the file. Your Java code is actually writing to the kernel page buffer, which is RAM, or which is memory, RAM memory. Then OS will, operating system will flush this to file. So that's how write operations on a file works. That's how the write operation on it. Your application only knows that the message has been, when we say a message has been committed, message has been returned to the file, the application only knows that it is been there in the kernel buffer. It is the OS responsibility to, on a timely basis, to flush this messages to the file system, to the actual file system. So internally what actually happens in Kafka here is, now the producer sends the messages to the broker. When we say the broker is committing or appending that message to this file, actually broker is has returned to the kernel page buffer, and internally the buffer will be flushed. Internally the buffer will be flushed by the operating system running on this Linux system. I mean the operating system running on this system. So you need not touch that. That configuration parameter should never be touched. So it is highly optimized, and the OS will take care of flushing the data. So usually what happens, the producer sends the data will be available in your kernel page buffer. Most of the time the request from the consumer is is I mean any request from the consumer is handled by the data in the kernel buffer itself. Messages are sent not by reading from the file. Messages are sent that are available in the kernel buffer itself. So that's how it is achieved real time. Real time data transfer is achieved by sending the messages that is available in the kernel buffer itself. So because of this reason, Kafka also requires high memory. It may be strange if you don't know this concept, if we don't know this concept, saying that Kafka requires high memory may sound a bit conflicting, but Kafka requires more memory. The reason is the reason is most of that memory will be used for kernel page buffer. Few lesser memory is used for running the broker daemon. Probably some 8, let's say 8 GB is allocated. Let's say your this system has 32 GB RAM. The system has 32 GB RAM. Somewhere around 8 GB will be allocated for the broker daemon. Broker daemon, whatever rest is remaining, whatever rest is remaining, 24 GB will be assigned for the kernel page buffer, so that more data resides in the memory for longer duration of time, so that requests from the consumers are handled in a real time fashion. Requests are handled in the real time fashion. It may happen that consumer may go down. Consumer may go down. It may take some 1 minute to come up. So when it comes up again, the data should still retain in the kernel buffer, so that you can handle real time processing. Even after coming back, it should be able to get the messages from the kernel buffer, and not from the mess. I mean to say, the file. So based on this time, how long a consumer will come back, how much time it will take to come back, based on this also this RAM can be configured. Because if it takes 2 minutes of time, you need to have more data in your kernel buffer for higher throughput. So you may have to increase your RAM size. You may have to increase your RAM size. So this RAM size can be, I mean, what RAM size is required for your Kafka cluster can be determined based on how much time you want to retain the messages in the kernel buffer. So if you want to retain for 1 minute, you may require certain RAM. If you want to retain messages in the kernel buffer for 2 minutes, you may require some more extra RAM. So determining the RAM depends on how much time you want to retain the messages in the RAM buffer. So those things you can also understand from whatever I have explained here. I think in one of the documents they have explained. I think in the Kafka Cloudera Kafka reference architecture they have explained it. It is a good document to understand these stuff. So I hope how real time is achieved is clear here. How the real time is achieved is clear. Most of the times, all the requests, the consumer requests are handled from the messages available in the kernel buffer. You will very less you will see input output, disk input output operations. So it all depends on how much RAM you have in your Kafka cluster. Not only you require more disk, you also require more RAM for your Kafka cluster. And they have explained it. I don't know why it is being given here for durability purpose. So I don't think so. This has to be. Let me confirm on this. They usually recommend not to touch this flushing interval time. Not to touch this. But let me confirm this. I mean, you can go through these things, and these are the things I wanted to discuss. How to optimize your Kafka cluster for a specific goal. I think most of the things I have covered here. Most of the things I have covered. But for more understanding, you can always go through these documents. This is a very good document for optimizing your Kafka cluster. So let's wind up the session here, and let's continue tomorrow. I think Monday. We'll continue on Monday, and we have some more things pending. We will Monday we'll discuss on consumer side. We'll discuss on consumers. We'll discuss on coordinator consumer, rebalancing, offset, and offset management. I mean, we may not be able to cover everything. Probably Monday and Tuesday we may finish the Kafka part. So let's wind up the session here, and let's continue on Monday. Thanks everybody. Have a nice day, and good night others, and have a nice weekend everybody.